All right, now there was a term not that long ago in a galaxy far, far away in which I had to come up with an exam, and the exam was feeling kind of hard, so I decided to make the loop invariant question easy to balance out, the dynamic programming question. And so, without really thinking, I threw this question in. And do you know what happened?
Half-fill.
It's too hard. In fact, I didn't realize how hard it was. All right? So now we're going to do, instead of insertion sort, we're going to do selection sort, and we're going to see how the loop invariant is different and how the proof's harder. All right? So in fact, in some ways, I'm going to almost tell you that the nuance of this proof is harder than I would want to give you on a test. All right? So it's funny because the example of the algorithm is easier than I want to give you on the test, but the nuances of the proof become harder. All right? So, all right, so what are we doing here? All right, let's go. This is good. I think we got something happening here. What are we doing? We're doing selection sort. So now, what we're going to have here is the input. The loop invariant is going to say we've split the numbers in the left and the right as we did before, and the numbers on the left are sorted, right? So that's what we had before, right? But now we're going to add a new constraint. The constraint is all of these numbers are smaller or equal to all of those numbers, right? So we have a stronger loop invariant. Everybody get that? And that part's pretty straightforward. I was expecting everybody to get that, right? These numbers are smaller than those numbers. We have a loop invariant. All right, so, and what's our step now? Right? What do we want to do? It's called selection sort, right? So what do? We find the smallest number here, and where does it go? It goes right there, right? So the work is over here. So we're taking the smallest number, we put it where it belongs. Everybody agree with the algorithm? It seems really straightforward. So everybody would say, yay, this is obvious, right? And maybe, actually, I don't think I gave everybody a bad mark here, actually. I take it back. I think everybody sort of did okay, because they gave a hand-wavy proof that if this is true, then this is true. And that's all we're really asking for, right? So in some ways, it's fine. What's the nuance is that actually, if you want to do a formal proof, there are more steps involved. All right. So here, let's do a more formal proof, right? What we're trying to prove is that the loop invariant's true, right? All we know is that these guys are sorted and these guys are less than those guys, right? And what do we know? We took the smallest number here and we put it over there, and now we need to prove this, right? We need to prove that these are sorted and that these are smaller, right? So let's do it. The one thing we need to prove two things over here, right? The one thing we need to prove is that the numbers on the new left are smaller than the numbers on the new right, right? Yeah?
Even if it's empty, eventually on the right side it's going to be empty, right? Everything's going to go to the left.
Yeah, so then when you get an empty set, you have to deal with flaws that exist from the empty. Here's a question for you. Is it true that every elephant in this room is pink?
Yeah, true. Wait, yeah,
Can you show me an elephant in this room that's not pink? No, so it's true. Right? So you have to know that to be able to handle empty sets, right? If one of these was empty, it would still be true that if this was empty, every number over here is bigger than every number over there. Why? Because there are no numbers over here to talk about. All right, so here we want to prove that every number here on the left is bigger, right? And maybe this isn't so hard. How do you prove it? Yeah, these ones are smaller, right? So we don't have to worry about them. All we have to worry about, only guy that moved is this one, right? So we have to make sure that this one is smaller than everybody over here, right? And why do we know that that's true? Because we took the smallest one, right? People see that? So it's not so hard. Anyway, what we're saying, the numbers on the left were sorted. The new number added to the end of the list came from the right, right? And where do we got smallest? Oh. Oh, sorry. We're not trying to prove that the numbers on the left are sorted. That was the wrong whole thing. Did I jump? We want to prove that these are sorted. How do we prove they're sorted? Well, they were sorted. We had this guy on the right. We know it's from over here. So we knew that everybody over here was bigger than everybody over here, so we can put it where it belongs. All right? That's one we're doing here. And hence, everybody got that proof? Now we're going to do the other one, which I didn't read right. Now we're trying to prove everybody on the left is smaller than everybody on the right. And how do you prove that one? You prove that it was the case, right? It was the case. The only one we moved is the 31, and it's smaller than everybody over there, so we're good.
So I don't know what was the difference between that slide and the other slide.
Well, I got it wrong too, so you're in good company here. Here we're trying to prove that the numbers on the left are sorted.
The left of the right picture?
So we want to prove that the loop invariant is true for this, right? So the two parts of the loop invariant. The one part is that these are sorted, and the other part is that these are smaller than these, right? So how do you prove they're sorted? Well, they were sorted. We added this guy to here, but we know he's smaller than everybody else. We know that he's bigger than all of these guys, right? Here we're using the fact that these guys are bigger, right? And in fact, it's kind of interesting that there are two facts, right? The fact that they're smaller and the fact that they're sorted. Right here, smaller and sorted. And we need to prove smaller sorted. And the way you do it is you use the opposite one, right? To get these, you assume these.
So you have a bidirectional proof?
Yeah, you have to prove them together, right? To know that these are sorted, you need to know that these are smaller. And to know that these are smaller, well, here we're using that this is the smallest. So it's not quite a crossover. But there's some crossover happening.
And so what was the difference on the second page?
The second page is proving that these guys are smaller, right? These guys are all smaller than these guys.
I thought that's what we just did.
These numbers are sorted,
Oh, okay.
right? The two things. These are sorted, these are smaller. You have to prove them both. Right? Everybody kind of follow that? I'm not saying it's so hard, I'm just saying it was harder than I thought it was going to be. Yeah?
The condition that numbers on the left were sorted is loop invariant, not precondition.
Oh, this has nothing to do with precondition. We're going from we know this is true at time t, and the x condition is not true in the code, to proving it's true at time t plus 1. No precondition. Yeah? No? Maybe so? What?
Why isn't there no precondition?
Well, we also have to do, something we also have to do is to prove that if the precondition is true and you do the initial code, you get the loop invariant. Right? We have to do that. But that's not what we're doing here. Right? So when we do that, what do we say? We say the precondition is that we have a set of numbers. Right? And what does the code do? The code puts the empty set here. Right? And now, is the loop invariant true? Well, are all these numbers sorted?
Yes.
We got no numbers. They're sorted. Are all these numbers less than these numbers? Yeah, because they're all pink elephants that aren't in the room. Right? Does that make sense? Everybody good?
Since we know they're already sorted, don't we already know that less is going going to be smaller than the right, because since they are sorted, we already know that the left is smaller than the right.
So two different statements, right? These numbers could all be smaller than these numbers, and these could not be sorted. These aren't sorted,
These are not sorted, but
right?
once we know that it's sorted on the left side, we already know that the right is bigger.
No, because if you go way back to our previous algorithm, right? Now, these are sorted, but they're not smaller.